Hi. Today we're going to build a beginner machine learning project. We'll start out with a 7-step process that you can use to build an effective project. Then we'll build an end-to-end project using Python and Jupyter Notebook. Let's get started. Now we can talk about the 7 steps that we'll need to undertake to build a complete machine learning project. Step 1 is to form a hypothesis. And a hypothesis is a statement that we can prove or disprove using data. In this case, let's make our hypothesis that we can predict how many medals a country will win in the Olympics using data. Once we have our hypothesis, we need to find the data to prove or disprove it. In this case, we can use data from the Summer Olympics. This dataset contains more than 2,000 rows, where each row is a single country in a single Olympic game. So as you can see, this first row is Team USA from 2008, and we also have some data on how they did in the Olympics. And the second row is Team USA from the 2012 Summer Olympics. Now let's go through the columns in this dataset. So the first column is the team code. So it's a 3-letter code that indicates which country participated in the Olympics. The second column indicates which year these Olympic Games took place. The third column indicates how many athletes that country entered into the Olympics. The fourth column indicates how many medals they won in the previous Olympics. So for the first row, which is for the year 2008, previous medals would indicate how many medals Team USA won in the 2004 Olympics. And then the final column is what we're going to try to predict. It's how many medals the given team won in these Olympics. So again, going back to our first row, you can see that Team USA in 2008 won 317 Olympic medals. Once we have the data, we need to reshape it to make machine learning predictions possible. In this case, we don't need to do a lot of reshaping, since what we're going to predict is the final column, the medals column, and we're going to use the athletes and previous medals columns to do that. So our data is already in the form it needs to be in, where we can pull data from a single row to make the predictions that we need. Sometimes data will be in a position where the target column, what you're trying to predict, isn't available in a single row, or the predictors, what you're trying to use to predict the target, aren't available in a single row. In this case, our data is clean and everything is available in a single row. So we'll be able to use the athletes column and the previous medals column to predict how many medals a team will win in a given year. Once we've reshaped our data, we can start to clean it. And cleaning the data involves making sure that our data is ready for machine learning. In this case, a lot of our data contains missing values. So if you look at the previous medals column, for some teams, we can't actually find a value for previous medals. And that's because that team did not compete in the previous Olympics. So ALB is Albania, and Albania did not compete in the 1988 Olympics. So there's no value for previous medals because previous medals is how many medals Albania would have received in the 1988 Olympics. So for this first row, previous medals is missing. Same thing for the other rows. These countries did not compete in the prior Summer Olympics, therefore we don't have a value for previous medals. Most machine learning algorithms cannot work with missing data. So our fourth step is we're going to need to clean the data to handle those missing values. And the fifth step is going to be finding an error metric that we can use to evaluate the performance of our machine learning model. So our machine learning model is going to create predictions. So we're going to predict how many medals we think a country should have earned in a given Olympics. And those predictions are going to be different from the actual medal counts. And we need a way to figure out if those predictions are good or not. And the way we do that is to use an error metric. The error metric we'll be using is called mean absolute error, and you can see the formula for it on the left. Don't be intimidated though, we'll break down what that formula means and how we're going to use it. So the formula can look a little complex, but I'll explain how it's actually going to work. So I just added a column to our table called error. So error is just the actual metals, so the value in the metals column minus the predictions. And if there's a negative, we just drop the negative sign. And that's creating the absolute error. So that's everything in the formula to the right of the sum sign, which looks like a big E. So that's all we're doing is subtracting the predictions from the actual values. And then after we do that, we go ahead and take the mean of all the individual errors. So what we do is we add up all of the error values and then we divide by the total number of predictions we made. And that gives us what's called the mean absolute error. So that's the metric we're going to use to evaluate if our algorithm is making predictions effectively. Step 6 is splitting the data. So we need to split the data because we want to train on one part of the data and make predictions on another part of the data. And the reason we want to do that is if we train the algorithm on the same data that we use to evaluate it, it's like the algorithm having an open book on a test. So if you're studying for a test and you're given a practice test to take, and you can memorize all of the questions on the practice test, if you're doing well on the practice test, it might just be because you've memorized all the questions. It might not be because you understand the material on the test. So what we want to do is give the algorithm a new set of data that it hasn't been trained on to make predictions on. And that new set of data will tell us how well the algorithm is performing. So we're going to train the algorithm on the training data and then test it on the test data. And we'll measure the mean absolute error. So how well the algorithm makes predictions on the test data. And that will tell us if we've built the algorithm properly or not. And then the final step, step 7, is the fun part, actually training the model. So we're going to use linear regression, which is a very popular machine learning model. And linear regression works with an equation. So if you look at the top left, the equation y equals ax plus b is the equation that we're going to use to train our model. And there's a simple example of how that can work below. So you see the axis, metals is on the y-axis, and previous metals, so metals in the last Olympics, is on the x-axis. So for example, if a country may have gotten 1 medal in the last Olympics and 3 medals in the current Olympics. And you see that at the 0.13 on the left. So a linear regression model will draw a line between the points, and we can use that line to make predictions. So you can see that we've now drawn a line, and this line is a linear regression line. And what this line does is it lets us predict new data using past data. So we've trained the slope of this line using the equation at the top left. So the equation at the top left dictates the y-intercept and the slope of the line. And we can use this line to predict data that we haven't trained it on. So for example, if a country got 6 medals in the last Olympics, we can look at the line and we can see that that corresponds to about 6 medals in this Olympics. So we would predict that that country would get 6 medals in the current Olympics. So for example, if a country got 6 medals in the 2016 Olympics, using this line, we might predict that they'll also get 6 medals in the 2020 Olympics. So the way that we build a linear regression is we train it using data that we already have, and then we use what we've trained, the line, to make predictions on future data. Now, the model we're going to train is going to be slightly more complicated than this model. This is what's called univariate or single variable linear regression, where we're only using previous medals, so the medals a country got in the last Olympics, to predict the medals they'll get in this Olympics. But we're going to do something a little bit more complicated in our actual model, and we're actually going to use 2 predictors. So we're going to use this equation instead, which enables us to use two predictors. So the number of athletes a country has entered into the Olympics and how many medals they got in the previous Olympics. So we're going to train a model that takes into account both of those factors, and then we're going to make predictions. All right, so that's the setup. And hopefully now you have a good overview of the steps we're going to take. Let's dive in and start coding. Okay, let's go ahead and get started. So the first thing we're going to do is we're going to import pandas as PD. And pandas is an amazing Python data analysis library. And we're going to use it to read in and explore our data. So we're going to read our data in. Teams.csv is the file that contains our data. And the download link is in the description if you want to go ahead and download that data. So let's take a look at the Teams data. This is similar to what we saw in the table in the introduction, except there's a few extra columns. Let's go ahead and remove those columns just to make this a little bit simpler. Those extra columns are columns you can use to continue building this model out on your own. But for the purposes of this video, I'm going to just take those extra columns out. So let's use the same subset of columns that we saw in the table earlier. With a couple of additions. So I'll explain the additions in just a second. Okay, so let's take a look here. Okay, so we have team, which is the 3-letter code for the country. We have country, which is just the longer country name. We have the year, so this is the year that the Summer Olympic Games happened. We have the number of athletes the team entered into the Summer Olympic Games. We have the average age of those athletes that were entered. We have how many medals the country got in the previous Olympics, and we have the number of medals the country got in these Olympics. So we're going to be trying to predict medals, and we're going to use previous medals and athletes to do so. So we're going to use two columns to try to predict the number of medals a country got in the Olympics. And before we dive in and do that, let's take a quick look to see if it's even possible to make these predictions. So what we're looking at here is the correlation between the medals column and the other columns in our data. So when we're building a linear model, we want to look for strong correlations between the column we're trying to predict and the columns we're trying to use to predict that value, because that enables a linear model to make good predictions, to draw the line in a place that makes sense. So these correlations are on a 0 to 1 scale, and you can see the correlation for athletes and for previous medals is very high, which indicates that, yes, we probably can use these columns to make predictions. Let's take a closer look at the graph of how these columns look versus the medals column, and we'll talk a little bit more about correlation. So we're going to import a Python graphing library called Seaborn. And then what we can do is use Seaborn in the pandas data frame to actually plot athletes on the x-axis and medals on the y-axis. And then we're going to use our teams data frame as the data source. And what we're going to say is fit regression equals true, which will fit a nice regression line like we did earlier in the intro. And we'll say CI equals none. If we don't say CI equals none, Seaborn will give us a confidence interval around the line, which is not what we want. So we can see that there is a rough linear relationship between the number of athletes a country enters into the Olympics and the number of medals the country earns, which makes a lot of sense, right? If you enter more athletes into the Olympics, you have a higher chance of winning medals. If you only enter one athlete, the maximum number of medals you can win is 1, whereas if you enter 1,000, the maximum number of medals you can win is 1,000. So this shows us that there is a relationship. As the number of athletes increases, the number of medals also seems to increase. And this is good news for us because we want to make predictions using athletes. So the existence of this relationship is great. Now we can look at a column where there isn't as strong of a correlation. We can look at age. So you can see there's a very, very weak correlation between age and medals. It's 0.02 out of 1, which is very low. Let's make another plot and look at the relationship between these two columns. So we'll say fitreg equals true again, and we'll say ci equals none. So let's go ahead and plot that. And we can see here, there really isn't a linear relationship between age and metals. So as age increases, the number of metals doesn't really increase. You can see when age is low, the number of metals is also low. And when age is high, the number of metals is also high. There could be an interesting non-linear correlation here, where if age is between 20 and 30, it seems like potentially the number of metals could be high, but it's hard to tell. This may be something worth investigating later on your own. But for now, we just won't use age as a predictor in our model. Now, one last bit of exploration we'll do before we go ahead and do the machine learning is we'll make a quick histogram to look at how many countries fall into each bin for number of metals they earned. So to explain this histogram, you can see a lot of countries, almost 2,000 in our data set, have earned between 0 and 50 metals in an Olympics. And there's very, very few countries that have earned a lot of metals. So our data is a little bit unbalanced in the sense that some countries have earned a lot of metals and most countries have earned very, very few metals. So this may impact the usefulness of our model and our accuracy, and we'll look into that later and see if this affects it at all. But it's usually a good idea to look at the column you're trying to predict, the target, and see how balanced it is. All right, now it's on to the next step. We've found the data, we've explored it. Our next step is doing a little bit of data cleaning. So I mentioned earlier that there are some missing values in our data, and we actually want to go ahead and remove those missing values. So what I'm going to do is first find the missing values. So what this code does is it finds any rows that have missing values. So let's go ahead and run that. And you can see there are a few rows, about 130, that have missing values for the previous metals column. And I mentioned earlier why the previous metals column might have missing values. So Albania, for example, didn't participate in the 1988 Olympics, which were the Olympics previous to this. So we don't have any data on metals that they received or didn't receive in 1988. Same thing with Algeria and Andorra and so on. So what we're going to do with this missing data is we're just going to drop any rows that have a missing value. So the way we'll do that is we'll say teams equals teams.dropNA. And that'll just remove all of these rows from our data. So we're left with 2014 rows, and previous metals doesn't have any missing values anymore. The next thing we're going to do is go ahead and split our data up. And because this data is time series data, right? Some rows come before other rows. We want to split it in a way that respects that. So we want to take the last 2 years of data we have, 2012 and 2016, and put them in our test data set, and take the previous years and put them in our trained data set. And the reason we want to do that is in the real world, if we're trying to predict who's going to win the most medals in the Olympics in 2024, we don't have access to data from 2028, right? We only have access to data from the past. So when we train our machine learning model, we want to respect the order of the data and make sure that we don't use future data to predict the past. So we're splitting up our training and test set here. And the reason we're splitting them up is we want to be able to train our model on the training set and then use a different set to evaluate how well the model is doing. And that's going to be the test set. We don't want to train the model on the train set and evaluate how well it's doing on the train set, because that's like giving somebody all the answers to the test before they take the test. We want the model to be evaluated on data that it hasn't seen before, that it has not been trained on. Okay, so we can look at train.shape, and we can see our training set has 1,600 rows, and our test set has about 400 rows. So that's an about 80-20 split of our data, which is perfect. That's very, very close to what the default split is. people usually just do a default 80-20 train test split. So this will give us a good way to train our algorithm and evaluate the error. Okay, now let's move on to actually training the model. So earlier we picked mean absolute error as our error metric. So we're going to use that metric to evaluate our model after we train it. So to train our model, we can import from sklearn.linearModel, we can import linear regression. And the linear regression class is going to enable us to train and make predictions with a linear model. So I showed you earlier what a linear model looks like. You draw a line and then you use that line to make predictions. So we're going to initialize our linear regression class, reg equals linear regression. And we're using scikit-learn, which is an amazing Python machine learning library that has lots of built-in algorithms that all have a similar interface. So you could easily switch from a linear regression to a different model. Now we're going to define our predictors. So these are the columns that we're going to use to predict our target. And our predictors are going to be athletes and previous medals. Then we're going to define our target, which, if you remember, our target was the medals column. So we're going to train a linear regression model to use these two columns to predict this column. Let's go ahead and run that. Now what we can do is we can call the fit method to actually fit our linear regression model. So we'll call the fit method, and we'll pass in the columns from the training data set that we want to use as predictors. So this is the data we're going to use to train the algorithm. And then this is the target. So this is the data, this is the target that we're going to pass into the algorithm. And the algorithm is going to be trained on the training data set. So let's go ahead and run that. Now that we fit our algorithm, we can use that to actually make predictions. So we can type predictions equals reg.predict test predictors. So you'll notice this, we're calling the predict method of our linear regression class, and we're only passing in the predictors for test. We're not passing in the actual values. And that's because we want the algorithm to create predictions without knowing what the actual answers are. So we're going to use this to generate predictions. Now let's take a look at our predictions. So this is a NumPy array, and it is kind of hard to read, but you may notice a couple of things. One, these values are not rounded, right? Which doesn't really make sense given our scenario. Our scenario is we're trying to predict the number of medals a country will win. And countries can only win a whole number of medals. You can't win a half medal. The second thing is that some of these numbers are negative, and countries cannot get a negative number of medals. So we're just going to do some quick correction to correct the model to just prevent any negatives and to round our numbers. And the easiest way to do this is to just manually correct it. So we'll just do a couple of things to actually rescale our predictions and make sure that they make sense. So the first thing that we're going to do is we'll go ahead and assign our predictions to a column in our test data frame. And this will let us just take a look at our predictions more easily. We can see them there on the right. And then what we'll say is test.loc test predictions less than 0 predictions equals 0. So what this is going to do is it's going to index our test data frame. It's going to find any rows where the predictions column is less than 0, and it's going to replace the predictions value in that row with a 0. So basically, if predictions was less than 0, it will be turned into a 0. Then what we'll do is we'll say test predictions equals test predictions dot round. Just to make this data make more sense, we'll round all the predictions to the nearest whole number. So we can take a look at tests now, and predictions make a lot more sense now. 0 is the minimum, and we can see that the values are rounded to the nearest whole number. Now what we can do is we can go ahead and look at mean absolute error. Mean absolute error. So we will import mean absolute error from scikit-learn, and then we can call the function and then pass in our actual values, which are the number of medals that the team actually won in the test set. And then we can pass in our predictions. All right, and we'll get a number back indicating our mean absolute error. Now, what does this actually mean? So this means that on average, we were within 3.3 medals of how many medals a team actually won in the Olympics. Now, whether or not that's a good value, let's find out. So we're going to dig a little bit deeper into the data set and investigate if that is actually a good error or not. So first, let's take a look at our medals column in a little more depth using the pandas describe method. And what this shows us is the minimum value in the column, the percentiles, and the standard deviation. So it's usually nice to just do a quick sanity check and make sure that your error is below the standard deviation. If it's higher than the standard deviation, usually something's wrong. Either you're using predictors that just don't give you any information to predict the target, or you mess something up with your model. In this case, things look okay. Our error is far below the standard deviation. Then what we can do is look team by team to see how our predictions look for different countries. So let's look at the USA. So we can see in 2012, the US got 248 medals, but we predicted 285. And in 2016, they got 264 medals, but we predicted 236. That's not bad, right? We're not absolutely correct, but we're not super far off. So we are about 40 medals off here, but in percentage terms, it's not that high of a percentage. And same here. The percentage that we're off is not very high. Now we can look at another country like India that doesn't enter as many athletes into the Olympics and see how we did there. So with India in 2012, India got 6 medals and we predicted they would get 7, which is good, right? We're pretty close in percentage terms. But in 2016, India got 2 medals in the Olympics and we predicted 12. So we're off by a factor of 6. And this is where mean absolute error can be very different for different countries on a percentage basis. So if a country only got 2 medals, an average error of 4 medals is huge, right? That's a factor of 2 either way. Whereas for a country that gets 300 medals, earns 300 medals in Olympics, an average error of 4 is not that big a deal, right? In percentage terms, it's pretty small. So what we can do now is look at our errors by country just to see how we're doing on a country by country basis. Okay, so this is just finding the mean, the absolute error. So we're subtracting our predictions from our actual medals and we're taking the absolute value. We saw the formula for this earlier. And we'll take a look at errors. So this is just the difference between our predicted number of medals and our actual number of medals. And I'll use the column in test instead of the predictions variable, because that's the one that we rounded all nicely. So this just gives us our difference between how many medals we predicted and how many medals were actually earned by the team. What we can now do is group this by team. So we can create a variable called error by team, and we'll say errors.group by test team. So group by is a pandas method that creates a separate group for each team, and then we will calculate the mean. So this will create a separate group for each team and then find the mean error for that team. So if we look at error by team, we now have how many medals off we were on average for each country. Now what we can do is we can look at how many medals each country earned on average. So we can do the same thing with the medals column. We can group it by team, and then we can find the mean. And this will tell us how many medals each country earned on average in the Olympics. And then we can find the ratio between our errors. Error by team divided by medals by team. Call this medals by team. And let's call this error ratio. Okay, so now we can take a look at error ratio and see what it is, if I run it properly. And we can see there's a lot of NAN values here, and this is because a lot of teams, the average number of medals they earn is 0. So we're dividing by 0, and we're getting a missing value. So what we need to do here is import, actually what we can do is we can say error ratio. So we can take only values that are not missing. So this gives us 102 countries where we don't have missing values in our predictions here. We also get some infinite values, so we need to figure out how to remove those as well. So for whatever reason, if a country has an average ratio of 0 medals, so if our average error was 0 and our total number of medals was 0, then we'll get an NAN while doing this division in pandas. But if instead the error by team is 1 and medals by team is 0, then we get an infinite value, like in this case. So we just need to clean up our infinite values as well. So what we'll say here is error ratio equals error ratio np.isFinite error ratio. Okay, and then I'll import numpy as np. All right, so now we can take a look at error ratio. Okay, so we now have 97 values. We've removed all our missing values and our infinite values. So that gives us only the countries that we have an actual error ratio for. And now what we can do is we can go ahead and create another histogram of this. And what this tells us is an error ratio of 0 to, let's say, 0.5 means that you are within 50% of the actual medal count. But in some cases here, our error ratio is 2 and above, which means that our predictions were twice as high as the predicted medals or half of the predicted medals. So it means that we're pretty far off the true value. So what you'll want to do to determine if this model works for your purposes is look through the error ratios for the countries that you want to make predictions for. And for some countries, the error ratios are pretty good, right? So for the US, we're within 12% of the true medal count. For Australia, we're within 36%. But for other countries, the error is higher, right? And we're much further off the true medal count. So whether or not this model is good depends on if it can do well in what you want it to do well in. So sometimes you need to go a layer deeper and get a little bit below just the mean absolute error or the all-in-one error metric and actually figure out what that metric means and how it breaks down among specific groups in your data. So in this case, if we wanted to make predictions for countries that tend to earn a lot of medals, we would do pretty well. And we can see this by typing error ratio.sort values. So countries that tend to get a lot of medals in the Olympics, like France, Canada, Russia, our error is pretty low. Whereas for other countries, which maybe we don't have as much data for or don't send as many athletes to the Olympics, our error is much higher. So for countries that send a lot of athletes to the Olympics, our model performs pretty well. But there is a lot we could do to continue to improve it if we want it. All right, so at this point, we've gone through the 7 main steps in building a machine learning model. And now we can talk about if we wanted to extend this, what we would do. So there's a couple of things you can do to improve the accuracy and performance of this model. So you can add in more predictors to the model. So you'll notice there are a few columns we didn't use. So that would be columns like events and age or height. So that's one option. You could try different machine learning models. So models like a random forest or a neural network to see if they perform better. You could go back to the original athlete level data and actually try to build a different kind of model. So the data that we're using, the teams.csv data, I actually summarized from a different athlete level data set. So we can go ahead and take a look at that data set. That's this athlete events.csv data set. And this data set has information about individual athletes in the Olympics. So each row is a specific athlete. And what you could do is build a model to predict if a specific athlete will win a medal. And you could add the results of that model together to figure out how many medals each country will win. And that model could be more accurate than a top down, just looking at the total number of athletes in a country model. So you could build a specific athlete level model. You could also try to reshape some of these columns. Some of these columns may have non-linear correlations with our target, with metals. So you could try reshaping those columns using different mathematical transformations to see if that creates a more linear correlation. All right. The final thing you can do is measure the error more predictably. So you can build a system like a backtesting system, which I've talked about in other videos, or another kind of system that can measure error across the whole data set, not just on a 20% subset of it. You could also train a model for different types of countries. So you could train different models for countries that earn low numbers of medals versus high numbers of medals, etc. So all of these ideas could help you build a more accurate model. Well, I hope this was a good beginner introduction to machine learning and that you understand the main steps in building a machine learning model. Thanks a lot for watching.